Okay, students, today we are starting with the thermodynamics part 2. Total thermodynamics we have divided into three parts. Thermodynamics part 1, which covers zeroth law and first law of thermodynamics. Okay, after that we have started with the thermochemistry, and those two lectures are already completed and already on the video lectures are uploaded. Okay, now it is time for the thermodynamics part 2. In this part 2, we are going to cover the chapters. We are going to cover the topics of the second law of thermodynamics and third law of thermodynamics. Okay. So with this, total thermodynamics will be completed from the basics to the advanced level. Let's start one by one. Okay. So here thermodynamics part 2. We will start with the second law of thermodynamics. Okay, so second law of thermodynamics is about the main up to first law of thermodynamics. It was concentrating only about the energy, how much energy will be released, how much energy will be required. Okay, that was only the drawback of the first law. Okay, first law was limited up to only energy, how much related and how much required. Okay, so but whether that reaction is possible at a given temperature or not, or at a given pressure or not, it was a doubtful situation before the second law of thermodynamics. Okay, so then second law of thermodynamics was needed to explain the feasibility, this is the normal daily life word we will use, feasibility. Okay, so that feasibility at the given conditions of temperature and pressure is called as a spontaneity. In thermodynamics we call them as a spontaneity, whether that reaction is spontaneous or not. If non-spontaneous, what is the problem? Okay, even second law of thermodynamics also was limited scope, have a limited scope in explaining it, but still it is better than the first law of thermodynamics. And we can't say second law of thermodynamics is enough. It is an extension. From the first law of thermodynamics, we will come to know about how much energy will be released. From the second law of thermodynamics, we will come to know whether the reaction is possible at given point of temperature and pressure or not, we will find out. And some more addition will be done. There are some drawbacks with respect to the second law, so that will be added up in the third law. So that means altogether we have to cope up with we have to merge the all laws together, zeroth law, first law, second law and third law. Then only the complete energy transformation. Thermo means heat. Okay, dynamics, that means movement. So thermodynamics will be completed only if you are able to attach all together in the proper sequence. Okay, so what does this law says? First of all, I think it is understood the necessity of the second law of thermodynamics. But what does it says? It is impossible to construct a machine that is able to convey heat by a cyclic process from a colder body to hotter body. This is a limited sentence. Okay, this is again, now it is extended, and with some examples also I will be giving. So you cannot always, when suppose if you are connecting the two bodies, one is at the 300 degrees Celsius, another is at the 200 degrees Celsius. Okay, so once they are attached with the thermally conducting material, always heat flows from 300 to 200, higher temperature to lower temperature. So with the that is what second law. And until unless on its own, it will always move from the 300 to 200, high temperature to low temperature. But if you are using a outside machine, okay, this was a cyclic process. Okay, so once you use outside agency, then it is possible. That means we can say this is non-spontaneous, this is spontaneous. Without the use of any external agency, if a process is occurring in only one direction, then it is called as a spontaneous process. I think spontaneous process definition is clear. It is a process which is occurs only in one direction without the support of external agency. Okay, so it will explain about the spontaneity of the reaction. A process which proceeds on its own without any outside help is called as a spontaneous process. Okay, so to understand the concept of spontaneity, first most important factor involved is entropy. Okay, so before explaining about the spontaneity, we should have some basic terms like entropy. Basic terms like entropy. Okay. Okay, entropy. So this is a part of the second law of thermodynamics. It is not complete, it is a part. To understand the meaning of spontaneity, the very required word is entropy. Okay. So entropy is a word, or entropy is a thermodynamic quantity. Till before entropy, we have measurement for the hardness of a body used to be measured in temperature, and heaviness of the body used to be measured with the help of the mass, and the size of the body was measured with the volume, but there was no measurement for the randomness or disorder of the system. Okay, so before entropy was given, so there was no measurement. Suppose if you take two substances, one substance is like this and another substance is like this. Okay, so what is the difference in quantity of these two? There was no quantity to compare, such maintaining the molecule in a proper pattern. Okay, so now the after introducing of entropy, we can say the entropy of this substance is more than this. Okay, so wherever the particles of a substance are arranged more randomly, then that substance is called as a more is said to have the more entropy. Okay, the substance where randomness is less or negligibly zero, then entropy will be minimum or zero. Okay, so it was a measurement for the randomness of a system. Okay, now what about the entropy? Entropy is a state function. So there are two functions in the first law only. Before first law only we have studied state function and path function. Okay, so any function which depends only on the initial and final state, but not how it is reached from the initial to final state, then it is called as a state function. Suppose this is a state A and state B. Whether it will reach from the A to B like this or like this, the entropy is going to be same. That means it is a state function. If it depends in this way, entropy is something, in this way it is entropy something, then we say entropy as a path function. But as it is independent, it is not depending on how it is reached from A to B. We are concerned whether it is reached to B or not. That is only the final decision. So that final state only depends. Then it is called as a state function. So our entropy is a state function. Okay, now how to calculate entropy? So entropy calculation is very simple formula, delta Q reversible upon temperature. Okay, so this was the main problem. People are not remembering this word. Okay, in the thermodynamics, until unless you don't concentrate on the small word, there are plenty of option occurs to be correct. Okay, so this heat required only we should consider at reversible condition only. Irreversible condition we don't take. Okay, so that I will try to explain through the graph, so that that clarification will be done. Okay, so where I have to use this formula, why I have to use this formula, why not some other formula, that I will tell you through the graphical explanation. Okay, so through the slides, that is the only advantage. Everything will be clear with the predetermined notes you will be having and well clarified diagrams you will be having. Okay, so the delta S is equal to, suppose if we have small changes, yesterday some was in previous lecture somebody was asking why we should integrate, sir. Okay, suppose if it occurs at a one stretch, then it is called as a irreversible. If it occurs in small changes, then it is called as a See, reaching there is only same, but it is done in the small steps. So these all small step must be added together. Integrate means combining lot of small things. Okay. So integrating, that means integrity of nation. That means joining the people of the nation. So like that, integration means joining small things to make it large. Okay. So here, if the heat amount is very small, then we will integrate. See, there is this people not aware there is a difference between the D and delta. When quantity is very small, then we use a term D. When quantity is comparatively large, then we use delta. Okay. So to get this delta, what we have to do, integrate the small changes. Then we will get the delta. Okay. So the Q reversible upon T. So after integrating that total small things are combined together, then it will be formed as complete delta. Okay. So final formula will be Q reversible upon T at delta S. Okay. Okay, here we are going to have sign convention. Simple, it is as good as work convention and sign convention. Okay. So heat is absorbed. Suppose, as I told you, delta S formula, according to that, heat is absorbed. That means Q will be positive or delta H will be positive. Therefore, delta S will be positive. Wherever you find delta, delta will be final minus initial. Delta will be final minus initial. So, if it is positive, what does it mean? Final is greater than the initial. That means entropy increases. So during any process, that is if it is endothermic, we can say entropy will be increased. Suppose heat is released, that means exothermic. So for exothermic, delta H will be negative, so delta S also will be negative. That means entropy will be decreased. Okay. So during exothermic process, as a thumb rule, as a combined simple sentence, we can say during exothermic process, entropy will be decreased. During endothermic process, entropy will be increased. Okay. Also, some amount of heat absorbed increases entropy, will be more at lower temperature. This is very important point. This was one of the advanced examination question. Okay. Entropy increase will be more at lower temperature. Suppose a system A is there. Okay. And identical system A is there, but I am writing it as a B, and it is at 100 degrees Celsius. It is at 200 degrees Celsius. Okay. So this was a small sentence taken from our NCRT, but they constructed a good amount of question from this small sentence. Okay. So 100 degree and 200 degree. So if I am giving same amount of heat, okay, same amount of heat, that increase in entropy, suppose this is delta SA, and here the increase in entropy will be delta SB. So according to this sentence, increase in entropy will be more at lower temperature. So even though both are given with the same quantity of heat, but increase in entropy will be more in A than B. More in A than B, because it is at the lower temperature. Okay. Increase in entropy will be more at lower temperature than at high temperature. Okay. Then if the temperature of system increases, then increase in entropy is always there, but quantity of increase will be less. Okay. So if the temperature of the system decreases, entropy decreases. So this was a previous and very old concept where questions used to be, but nowadays lot of complicated questions are there, how to identify the entropy increase or decrease. So that I have made some small notes. Tricky problems are given into the simple solutions. Okay. So let us see the next slide. Okay, criteria for spontaneity. So now to understand the second law of thermodynamics is all about Okay, so whatever the entropy I have told you, that was only to support and explain about the second law of thermodynamics. Okay, so now we are back into the thermodynamics second law, which was only for the spontaneity. So first law of thermodynamics is basically law of conservation of energy. It was concentrating on energy, but no restriction on the way of energy flow. Like I told you, whether the heat will be from 300 to 100 or 100 to 300. There was no clue or no explanation in the first law of thermodynamics. Okay, so that's energy flow from higher to lower or lower to higher was not as per the first law of thermodynamics, but natural process. Naturally, what we see only one direction. Okay, so the chemical reaction also same, will tends to follow from minimum direction of minimum energy. Suppose if we say A is giving product B, so once it is happening means this A will be having more energy, B will be having less energy. The reaction will be more probable if it is exothermic. But we see many reactions are increase in entropy. Okay, so a reaction will occur if delta H is negative or delta S will be positive. So up to now, this rule, whatever I am saying, this is up to now. As soon as I will keep on adding the new law and new points, this may not be completely satisfactory. At the final of this lecture, I will give you a complete table to whether identify all conditions of zeroth law, first law, second law, and third law. Combinedly, I will give you. That will be the final decision to identify whether a reaction is spontaneous or not. Okay. So till last table is going to be the very, very important table because it is combination of all the three parts. Okay. So as per now, for a reaction to be spontaneous, delta H must be negative, delta S must be positive. So we cannot say that this will be happening only that. Okay, only that process will be spontaneous. But as of now, it is considered like that. Okay. So, but endothermic reaction, which is delta H is positive, also takes place. So there are also reactions in which decrease in entropy, but still they occur. Okay, these are all answered by the next law, that is third law of thermodynamics. Okay, so it is only added according to the first law. The reactions are occur when delta H is negative. Okay, now it says delta S is positive. Then finally we will combine within the both of them in form of what? Free energy. Okay, so what is that free energy? That we will learn in the future slides. Okay, now this already I have explained, and here I wanted to emphasize in this slide is a thermodynamic energy available for us. Okay, for a useful work, thermodynamic process such as energy conversion devices. So that means if we have 100 kilojoules of energy in the system A, and we can never and ever convert total 100 kilojoules of energy into work. Okay, because some will be utilized in the disorderness, some will be utilized in the making the system disorder. How much will be converted used in the making it disorder is formulated by this formula. I have already told you, this is a new add up in this slide. Okay, and dimensions, units. Okay, so here in the numerator you find what? Heat. So therefore it will be joules, and in the denominator temperature, so Kelvin. So international SI units. SI units are delta S is equal to delta U Q delta Q by T. Therefore entropy units are joule Kelvin inverse. SI unit of entropy are joule Kelvin inverse. Okay. Now let's see the next slide. Entropy is a measure of. So as slowly a lot of things will be added up. Then finally we reach to the third law. So entropy is a measure of unavailability of system energy to do work. Okay. Suppose if we have 24 hours of a day, so but we cannot make all 24 hours into the work. Okay, so something is required for maintaining some relaxation. So like that, relaxing energy is called as a entropy. So it is also a measure of disorder of I. So that means entropy can be now defined in two different ways. It is a measure of disorderness or unavailable energy. Suppose out of 24 hours, you are able to work properly with utmost sincerely 8 hours. So that remaining will be, I think, 16 hours. Okay. So that 16 hours will be entropy. Is it understood? So whatever the unassigned energy which cannot be converted into work, useful work, is called as a entropy. Okay. So useless work, you can say useless work, and measure of disorderness also. So the measure of disorder, entropy is a measure of disorder. Higher the entropy, greater will be the disorder. So it is a parametric state of disorder. Okay, and but at what levels? Atomic levels, ionic levels, molecular level. So greater the disorderness, greater will be entropy. Okay, though for process which do not involve heat change, suppose we cannot find out. If we have an option, we will go for that option. If delta H is negative, then it will be spontaneous. But we don't know about the enthalpy, heat change, or there is no heat change at all. Then what is the criteria for us? Entropy is the criteria. Okay, criteria for prediction of direction of spontaneity have been derived through mere observations. There is no theoretical, only process. Suppose if a process is carried out on its own, on observation, without anybody help, then it is called as a spontaneous. So for spontaneity, second law of thermodynamics defines as following statement. This is very, very important, and mainly you have to remember this formula. Remember this formula. Okay. So for an isolated system, in an isolated system and in non-isolated system. Okay, isolated system, open system, and closed system. Already very first point of the first law of thermodynamics. Already I have explained. So in an isolated system, increase in entropy, direction of spontaneity. Whichever direction. Suppose A is ready to move B and ready to move C, but during the A to C it is entropy is increasing, A to B entropy decreasing. So A to C is spontaneous, A to B is non-spontaneous. But for non-isolated system, once I say non-isolated means it have tendency to share something with the it have tendency to share something with the surrounding. So now the surrounding entropy also comes into the picture. So total entropy will be entropy change in the system plus entropy change of the surrounding. Okay, so then we will decide about the direction of spontaneity. Okay, so for a reaction to be spontaneous, delta S must be positive. So here delta S will be should be of system plus surrounding, should be of system and surrounding. Okay, for which it one, this is for non-isolated system. If it is isolated, we will consider only one and only system because it is completely free from the atmosphere or surroundings. Okay, so in this chapter we call them as a surrounding. Okay, so for a reaction, entropy of a reaction and entropy of a process, we have two different things. Entropy of a reaction will be, for a reaction normally we will use the term called as a delta H. Okay, so entropy of surrounding will be equal to Q of the surrounding upon T. So suppose surrounding is gaining, that means system will be losing. Surrounding is losing, system will be gaining. That's why you will find opposite sign here. Okay. So delta H surrounding minus delta H system upon T. This is for reactions which occur at, very, very important. Here constant temperature is required, and for an enthalpy require constant pressure. Okay, so this is for the surrounding. So same way delta H total is equal to delta S system minus H system by T. Okay, for surrounding, actually we cannot accumulate all the surrounding. Surrounding is a vast area. So then what we will do, we will take system into consideration. We will take what? System into consideration. From the system, we are calculating the delta S and substituting here. Okay. So this is formula. Just you remember this formula. So need not to go at this stage of examination also. You will require this application substitution only. Okay. Enthalpy of system is this. Entropy of system is this. Find out a total entropy change of surrounding and system. Okay. Then for a process, that means it is a physical process. So delta S surrounding. Delta S surrounding will be Q surrounding by T. Same formula, Q system. Okay. So but it is for process. So we cannot say reactant and product. We cannot say reactant and product. Okay, now next prediction of sign of delta S. For the reactions I am telling you. So first already I told you with change in temperature at constant. See these conditions. These are all specially designed as per the latest pattern of question. People are not able to answer the questions because there is no perfect sentences relation to identify the entropy changes. Okay, when volume is constant and temperature is increased. So with the increase in temperature, entropy increases. Okay. And when constant temperature and volume is changing, so volume is increasing, therefore entropy also will increase. Wider the system, wider will be the randomness. Okay. More will be the randomness provided temperature is constant. Suppose it is very simple and very known to most of the students. Phase changes. If the same substance, it is in the solid state, less entropy, liquid, less entropy, and highest entropy found in the gaseous state. Okay. So this is about the entropy changes. Some only. I am giving you some more relations which are directly useful shortcuts for the examination questions. Okay, next one. For a chemical reaction, entropy change. So if only solid and liquid, okay, then changes will be very small because you find solid are more disciplined. So they will be arranged more properly. And liquid also some randomness will be increased, but that will not be that much increase when it is converted into gaseous state. Okay, so, but this is liquid state. But if it is in gaseous state, then randomness will be more randomness. So, more and you will find a lot of increase in randomness when it is changed from the liquid to gas rather than from the solid to liquid. Okay. So, this is about the solid, liquid and gas. So, if it is from solid to liquid, entropy increases, liquid to gas, entropy increases, and this quantity is more in the liquid to gas, less in the solid to liquid, and in the opposite side the entropy will be decreasing. Gas to liquid entropy decreases, liquid to solid entropy decreases. Sometimes even in the solid also, if you have arrangement difference, then entropy will also change. So entropy of a graphite is more than the diamond, because in diamond you will find each and every carbon is perfectly attached to 4 carbon through the strong sigma bond. But in graphite it is not so. It is attached to only 3 carbon atom with the proper sigma bond, but third bond, fourth bond will be weak van der Waals bond. So because of this, randomness will increase. Okay. So even in the crystalline system, we cannot say, in the solid system also, we cannot say entropy will be same. Even same substance, if it is in amorphous, entropy will be more, crystalline entropy will be less. Okay. So this is about the entropy in the solids. Now, if you are given with a reaction and asked to write the entropy change, then you will depend on the gaseous product. If entropy, number of gaseous products are more, then delta S will be more. If number of gaseous products are less, delta S will be decreasing. If there is no change in the, this is only for gases, this is only for solid and liquid. Okay. So delta Ng will be equal to 0. It does not mean that delta S will be 0. Okay. No, it is not like that, because as I told you, in the gas itself, the formation changes, structure changes, then entropy will also changes. So this is the most of the people are as a tendency greater than, less than, equal. No, it is not equal. It is not equal. Okay. So as in the previous slide, I said solid to delta Ng is 0 does not mean that delta S will be 0. Okay. So it's not, because even same molecule, suppose it is also gas, it is also gas. But randomness in 1 mole of nitrogen dioxide will be more than randomness of nitrogen monoxide, okay, or nitric oxide. So we here delta Ng will be 0. Initially 1 mole of NO was there, after that 1 mole of NO2 is there. So gases with no change in the gaseous moles, but there will be change in the entropy because of the structure. Okay. So here methane and ethane. So then for molecules having same atomicity, atomicity means number of atoms per molecule, entropy will be more for the substance having more molecular mass. Okay. So suppose A is having 4 tetraatomic, B is also having tetraatomic. Okay. Then entropy will be more for the substance having more molecular mass. Suppose molecular mass of B4 is greater than molecular mass of A4. Okay. Then this entropy of B4 will be more as compared to entropy of A4. These are all done on the experimental results. Okay. Are mere observations. Then for a reversible process, it is just already I told you, for a irreversible process, entropy of universe increases, but it remain constant in reversible process. Entropy remain constant for reversible, but irreversible entropy will increase. Okay. Reversible, so forward increase, backward decrease. So entropy will be, change in entropy will be constant. Okay. So that's what C. Delta S system plus surrounding is equal to 0 for reversible process, but not 0 for irreversible process. Okay. So if I combine both of them, greater than or equal, equal is applicable for reversible, greater than is applicable for irreversible. Okay. So now let's go to the next slide. Okay, next is about the third law of thermodynamics. Okay, so third law is thermodynamics is not nothing new. It is only combination of the all available things. It picked up something from the first law, it picked up something from the second law, clubbed together, then it gave the third law of thermodynamics. Okay, there was a problem in the second law of thermodynamics, which says that entropy of any substance we can never find out. Okay, because entropy is only randomness. We will say whether it is good or bad with comparison to somebody. So, but who is there to compare? Nobody. Okay. So then this third law of thermodynamics is given. Okay. So this gave a reference for comparing the randomness. So what is that reference? At absolute zero. Here absolute zero means it is not mass. It is absolute zero means it is temperature. Absolute zero means 0 Kelvin. Okay. Now, 0 Kelvin is technically termed as absolute zero. The entropy of a perfectly crystalline substance is taken as 0. Perfectly crystalline substance is taken as 0. See, temperature is kept lowest possible and perfect word is used and even crystal word is used. So they left no chances to give randomness. Okay, randomness will be more in amorphous. So for that sake only they have taken crystalline, and after that there may be some defects in the crystal like amorphous, sorry, uh, Schottky defect and Frankel defect. So to avoid that, that perfectly word is used. So if temperature is increased, then molecules kinetic energy will increase. So they will start roaming here and there. That's why what they have taken absolute zero. So after taking all precautions, there is no chance of the randomness. Therefore, uh, at absolute zero, entropy of a perfectly crystalline substance is taken as zero. Okay, so that means at absolute zero, every crystalline solid have no randomness. No randomness means entropy you can take it zero. From that you can compare. With respect to that you can compare. Okay, so by virtue of the third law, absolute value of entropy. Absolute, actually we cannot find out the absolute value of enthalpy. We cannot, sorry, absolute means this delta will not be there. So H we cannot find out, and why? Because it depends on the U. U you cannot find because it is sum of the many energies. But because of this third law, now we can find out absolute value of entropy. Okay. So earlier the entropy we can never find. That dream came true after the discovery, after the proposal of the third law. How you will find out? By this formula. Okay, so entropy of the substance at 0 Kelvin is 0, and slowly how much it is increasing to the given temperature. You will add up. Add up means integrate. So therefore entropy at any temperature, entropy at any temperature will be entropy, absolute entropy. This is not change in entropy. Change in entropy will be delta S, absolute entropy will be S. Okay, so change in entropy, you already we have formulas delta H Q reversible by T. So here entropy at the given point of temperature will be right from the added up from the 0 Kelvin to, suppose I want entropy, absolute entropy of some substance at 23 degrees Celsius. So I will keep on adding up to the 23 degrees Celsius right from the which temperature, right from the which temperature. Okay, this was the one of the previous question, that's why I asked. Okay, this was one of the previous question, that's why I asked. So people answered 0 degrees Celsius. No, it is not 0 degrees Celsius. It will be from minus 273.13 degrees Celsius. So you will start integrating, integrating from minus 273.13 to 23. Because that's why I told you, very important in chemistry. After coming out also people don't realize that they have done mistake. Okay, mistakes are very closed, very unfortunate. Okay, so they will come only after the result day. Okay, so then they will cross check. So 0 Kelvin will be 0 minus 273. So you will start integrating from minus 273.13 to plus 23 degrees Celsius. Okay. So this is how third law of thermodynamics enabled us to find out the entropy of a substance from its reference of solid crystal, perfect crystal at absolute 0 Kelvin. Okay. Okay, further after formulating the third law of thermodynamics, then mathematical form is given in the form of the Gibbs free energy. Now it is a final decision, final destination for finding out the spontaneity. He simply what he have done, he is just like a mathematician. He added all together what we have. Okay, so here Q can be Q can be according to the first law of thermodynamics, this one. Okay. And according to second law of thermodynamics, this one. So added all the things together. Then we got free energy. Okay. This will be more clear in the next slide just for the time being. Okay. So G will be H minus Ts. But problem is with what? H. We cannot find out the H value. Okay. So first of all, what is Gibbs free energy? It does not mean that energy will be free. No, it is free for doing the useful work. Okay. So amount of energy, like I took the example, we have 24 hours. So, but we can do proper work only for 8 hours. That 8 hours will be our G. Understood? And that remaining 16 hour will be entropy. Is it understood? So then you will get useful work. Total available out of this much wastage, this much will be useful. See, this was the total available, this much wastage, then you will get this much useful. Like 24 hours minus 16 hours for relaxing and enjoying, and 8 hours of useful study. See, is it understood how this formula came? So IUPAC recommended name for this useful energy is Gibbs energy or Gibbs function. Okay. So Gibbs energy is its capacity to do a non-mechanical work. Okay. Or delta G is a measure of non-mechanical work done on a system. Okay. So very rarely this word is used, but I want that you should be aware of. People are aware of useful work means delta G. So, but it is also termed as, terminology is different, but meaning is same. Non-mechanical work done. Okay. Okay. Next, I've seen many people are losing their marks just because of the units. Okay. In that formula, U is a internal energy, unit must be in joules. P is a pressure, units must be Pascal. V is volume, unit must be. I am following which system? System International, SI system. Okay. At this day also, if I ask how many basic units are there in System International, many of them are not able to answer. For the namesake, they are preparing for the very highly advanced examination like MIT preparation. They started preparing, and they started preparing for IIT, but they lose the very basic. How many how many units are then basic crystals? Sorry, basic units, and what are the derived units that they are not able to concentrate. So that's why I wanted to emphasize here. If possible, I will make a very basic. Actually, this is not part of a chemistry. It is part of the all science subject. It is going to affect your marks in all science subject. So that I will give you with the complete details. Okay. So V is the volume in meter cube. So people are in habit of taking in liter and answering. Okay. So V is volume in meter cube here. T is the temperature in Kelvin. S is entropy. Just now I have told you joule per Kelvin. H is enthalpy in joules. Okay. So these are the some basic unit required to be substituted in the formula. So before substituting in the above formula, make sure that they are transferred into this SI units. Okay. So let's see the next slide. Okay, next slide. This is about formula. Just now I told you delta G is equal to H minus Ts. But the problem is that we cannot find out the absolute value of enthalpy. Then remedy, what is the remedy for not finding? If you are not able to find, it is not final, it is not stop. It should not stop you. Okay. So then we will apply the delta. There is no problem with the delta. Delta is only heat given to the system, heat liberated from the system by maintaining the pressure as a constant. So we can easily calculate the delta H. So we will apply the T delta S. So but during the derivation only I told you this temperature will be maintained constant. So If it is properly mentioned that temperature is constant, you can omit this term S into dt. Okay, if not mentioned, then you can use this complete formula. Okay, now if delta S is total, delta S total is greater than 0, that means delta G will be less than 0, then spontaneous. So finally we got all the three conditions. For a reaction to be spontaneous, delta H should be less than 0 or negative, delta S should be positive or greater than 0, delta G should be less than 0. Okay, these are preliminary conditions, but there are some contradictory conditions also that I am going to give you in the next tabular form. Okay, and I will explain through the graphical form, because graph questions are more occurring in the recent days in the advanced examination. Study of the graph in the thermodynamic terms is very important. Okay, so delta S total is 0, delta G system will be 0. This is at equilibrium. See here, delta S total I am talking about, not about the system. Okay. So small observations are very much required, because if delta S system will be there, it may or may not be 0. 90% also cannot be taken as 100%. Okay. Similar topic we have done in the enthalpy changes also. Enthalpy changes during the phase transition. Same we are going to apply here also. Solid, liquid and gas. So solid to liquid, melting. So that time we will take delta H melting here. Especially this is very important. Only at melting point this formula is applicable. Suppose in the water, we can apply this formula only at 0 degrees Celsius. Don't start applying up 2 degrees Celsius, because at 2 degrees Celsius, the main condition of application is it should be in equilibrium. So at 2 degrees Celsius, it is not in equilibrium. So entropy change during melting at constant temperature. The temperature will be melting point. Same is applicable for the boiling point. Same is applicable for the transition. Okay, this is an added up other than the enthalpy. Okay, so why I am taking this, because in the graph we are going to start from the right, from the perfect crystal at 0 Kelvin. So after that it may change from one crystalline form to another crystalline form. That condition it is going to be very much useful. Okay, so this is about the entropy changes in the different phase changes, entropy changes in the different phase changes. Okay, now let's go for the graphical representation. Okay, so here what is the axis? Whenever you start studying about the graph, your concentration should be what is taken on the x-axis, what are its particular units. Okay, here what is the units of the temperature on x-axis? How many of you are aware of this? So here temperature must be in Kelvin. So recently in the 2020 first session only, they have modified this and changed this starting point below the 0 degree Celsius. So these are all the traps. I don't want that you should be in the traps. So Kelvin, if it is mentioned, it will start from the 0. If it is in the degree Celsius, recent 2020 first session, there was a question according to this. Okay, so people started calculating as for it is 0. So 0 degree Celsius is not final to be substituted. Okay, so if you make such mistake, instead of 4 you will get -1, 5 marks will you may land up from the NIT to a private college. It will cost you some lakhs of rupees and ruin your complete career. Okay, so minute things, minute observations are required. Now here 0 Kelvin to some solid state. Okay, see here, this is vertically up, perpendicular to the x-axis. What does it says? This is the temperature where it is constant. At this place only, that formula I told you, delta S is equal to delta H upon T. Here what will be the T? Melting point. Is it understood? From here to here again, temperature will keep on changing. From here to here, you are not supposed to use this formula. Okay. From here to here, you are not supposed to use formula. But here you can use this formula. Here you can use this formula, but not before this, but not after this. Is this graph careful where the examiners are going to trap you with the wrong options? Is it understood? Any doubt about this? You can ask now. So these are the collection of formulas for the entropy change. Here you have to be very observative. It is of the system, it is of the surrounding. See, most of the places they are not same. Okay. Why they are not same? Irreversible, irreversible. Only in the reversible condition, delta S total will be zero. Okay. See here formulas itself are different. So when you add both of them, you will not get as a zero. Okay. So make a practice these formulas. So at least try to write 4 to 5 times randomly. Discuss with your friend. Make it as a quiz among yourself. That is the best way to learn these formulas. Okay. You will ask your friend about reversible isobaric formula in surrounding system, and he will ask you some question. That way, this is the only method to remember these many formulas, because all are confusing. Confusion does not mean that you will not attempt. You will attempt in a more careful manner. Okay. Now let's go to the next slide. These formulas derivations already given. You can practice if you get time. Okay, now most anticipated question of this time. Okay, as this time all are aware that this time IIT Kharagpur is preparing the examination paper. So here two gases, mixing of two gases, entropy change. You will find rarely in the books. So try to note down this. Okay, entropy change during the mixing of gases. So once two gases mixed, we have studied in the states of matter, that is different. Here during mixes of gases also entropy changes. Okay, because two things are mixed, then randomness will be more. Okay, but how much randomness it is increased, then it can be calculated by this formula. This derivation also already we have done well before, but formula you can remember for time being. Okay, so this is the main formula. R means universal gas constant, Ni. So actually this derivation was made only by taking two gases, but it does not mean that only two gases will mix. So three gases, four gases, five gases, then mole fraction of Xi, that is individual gas, and log Xi, it is number of gases. Okay. So this formula you have to remember, then we will solve the numerical based upon formulas. Okay, in the numerical session. Now let's go to the next slide. So calculation of entropy of a substance. Finally, we are collected the first law, zeroth law, and third law. Okay. Second law. So third law of thermodynamics is also known as Nernst heat theorem. Okay. So many of you are surprised. Nernst you will find in electrochemistry. Nernst also got involvement in the thermodynamics also. Okay. So all substances have same heat capacity. Many of the people are having doubt about the heat capacity. Heat capacities are total heat capacity, specific heat capacity at constant pressure, constant volume, molar heat capacity at constant pressure, constant volume. But here I am talking about the simple heat capacity at 0 Kelvin. They have the same heat capacity. But heat capacity of every substance is 0 at 0 Kelvin. Okay. And entropy of a perfectly crystalline solid is 0 at 0 Kelvin. Okay, now next we will go for the next slide. This is the table I was talking about, which is a club of the all the three laws. Okay, so some things are taken from the first column is taken from the first law of thermodynamics. Second column is taken from the second law of thermodynamics. Now finally it is the application in the third law of thermodynamics. Okay, so this is formula what we have used. Delta G is equal to delta H minus T delta S. Okay, so here delta G sign and delta G for a reaction to be spontaneous, delta G must be negative, delta S must be positive, delta H must be negative. So contradictory conditions we are talking about. Okay. So first condition, delta H is negative. This is negative. Delta S is positive. This is positive. Positive into negative. This total term is going to be negative. Two negative will be added up. You will always get delta G negative. So once delta G is negative, therefore the reaction is spontaneous. Okay. Reaction is what? Spontaneous. Like that you can calculate just by substituting here. Suppose if I substitute delta G positive, delta S negative, so negative into negative it will be positive. So when you add two positive things, you will never get a negative thing. Therefore delta G will always be positive. Once delta G is always positive, so total reaction will be non-spontaneous. Reaction will be what? Non-spontaneous. Okay. So this is what I was talking about, the contradictory condition. Okay. So if delta H positive, it does not mean that it is non-spontaneous. Delta S is positive, spontaneous. Contradictory condition, opposed condition is delta H. It is positive here. Okay. So still it is spontaneous. But what is the other condition it should meet? At high temperature. Okay. So delta H positive and delta S positive, the reaction will be spontaneous only when temperature is high. So that time it will be spontaneous. Otherwise it is non-spontaneous. Another contradictory condition is fourth column. At low temperature, when both are negative also problem. That time contradictory problem will be from the entropy side. Contradictory problem will be from the entropy side. In the previous fourth row will be contradictory with respect to the enthalpy. Third row. Okay, third row is contradictory problem is from enthalpy. Fourth row, this row is the contradictory problem is from the entropy. So, but entropy problem will be solved at low temperature. Enthalpy problem will be solved at high temperature. Okay. So this table is very useful and this formula is very useful. At least this is a basic formula. Okay. Okay, next one is relation between equilibrium constant and Gibbs free energy. Okay, so there are lot of formulas, all formulas already you might have studied in the equilibrium. Okay, so but it is somewhere thermodynamic terms are used here. So interrelated, topic related questions, cumulative questions will be there. That's why this equilibrium questions related to the thermodynamics formulas are revised here. So delta G R is equal to delta G naught R RT ln Q. This is at non-equilibrium condition. Okay. If equilibrium, automatically this delta G is going to be 0 and this Q will be substituted with equilibrium constant. This is relation between the equilibrium constant and equilibrium delta G. Similarly, enthalpy change already done. This is the Kirchhoff's equation related to the temperature. At temperature T1, equilibrium constant K1. At temperature T2, equilibrium constant K2. This is the enthalpy change. Because of this term only, we are studying this in this session. Okay. Now let's see the next. Okay, if you have any doubts, you can ask me. I hope all these topics are understood and maintaining proper notes is very important before going for the numerical session. Let's start with the numerical session.